Okay, let's get started for the last lecture for today. So is everybody already booted into Linux? So we're good to go in Linux. Next we'll be looking at OpenCV, so an image processing library. A lot of research is done with OpenCV, anything to do with image processing, tracking, video analysis, and so on. OpenCV is a very widely used library. So we'll start off with a little bit of an overview on what OpenCV is, and then we'll look at some of the modules it includes and do some basic operations using OpenCV. So first of all, what is OpenCV? Well, CV obviously stands for computer vision, and it's quite a mature, quite an old library for image processing. It was written in C++, but there's wrappers for lots of other languages like Python, which is what we'll use today since we've just had a lecture on Python. And but there are other languages you can use like Java. I believe there's some MATLAB compatibility as well. There's a module for MATLAB. So the current version is 3.4.1. I'm mostly familiar with 2.4, but they don't. The interface changes quite a lot between major revisions, so you kind of have to keep up to date. The website for OpenCV is here. They claim they've already exceeded 14 million downloads, so it's a very widely used library. Okay, so next we'll look at just a very brief history. So it was first launched in 1999, so that's long before I was even using computers, I think. So it was originally launched by Intel. They wanted to have a library which everybody could use without having to reinvent simple stuff like loading images. Because before OpenCV, everybody wrote their own interface for images and storing them in different kinds of matrix containers and so on. So OpenCV the goal was to standardize all of that kind of stuff. Also, they wanted to make really optimized code. So if you think about the time, around 2000 when they first released it to the public, computers were getting a lot faster very quickly at that time. So image processing for real tasks like face detection were becoming a possibility, whereas before that it was still quite difficult, just because the hardware was slower. OpenCV 2 coming along in 2009 was a really big step for OpenCV. The interface, I think OpenCV 2 is where the Python wrappers started becoming usable, and it really took off, I think, around the mid-2000s. So it's always been open source, it's always been free, but it was always the development was heavily done by Intel and a group of Russian developers as well. Then in 2012 it was taken over entirely by OpenCV.org for all of the support and so on. But interestingly, they've kind of gone around full circle, because this group, who've done, although it's open source, do most of the development, they've been purchased by Intel just recently. So Intel's back in control. There's lots of information on the website, opencv.org. You can download all of the source code yourself, lots of tutorials and so on. The API reference is very in-depth, so every function has got lots of information about it there. There's also Japanese documentation too, so it's pretty easy to get into OpenCV. Now, I keep mentioning that it's free, but it's a really important point that you can go in, you can take one of the modules, you can take the code out of the module, you can play with it, you can change it, and then if you make something really cool, you can actually even make a pull request. In other words, you can propose for your code to be included in the next release of OpenCV, because it's all open. And you've got lots of people working on various different aspects of OpenCV. The BSD license is one of the most liberal licenses in software development. So Apache 2 BSD licenses are very, very, anybody can, if you use that code, you can use it for anything you like, as long as you include that license with any code that you produce based on it. Because a lot of code that used to be included in OpenCV now has patents associated with it, there is another module of OpenCV called the non-free library, and that includes non-free, so non-open code, which you can still use for research purposes. If you want to use it for a commercial project, then you have to get in touch with the owners of the patents. But for example, image feature extraction, there's quite a few patented methods there that people still use every day for research purposes, but if you took them out of OpenCV entirely, it would be a real shame. So they've left them in there, but you have to download that separately and compile it separately. Okay, here are some of the things that OpenCV is commonly used for. Image processing is a very general term, but more specifically, object recognition, so things like face detection. You know, in Facebook now, it automatically recognizes faces in your images and asks if you want to tag people. That kind of stuff. I don't know if they're actually using OpenCV, but there's a very good chance they are. Motion tracking, that's motion tracking and that kind of. I used OpenCV a lot for some motion tracking problems with autonomous driving research. So you look at, that's another area which is a hot topic at the moment. There's a lot of image processing in autonomous driving, and OpenCV is a very useful tool for that kind of stuff as well. Human-computer interaction, so like gesture recognition, recognizing when someone's waving and then having a system which can recognize that and react accordingly. And there's just anything you can imagine that you want to do with a camera connected to a computer, OpenCV will help you. There's no two ways about it. So now let's have a look at just a brief overview of the modules. So some of this is kind of a little bit repeated, but this is kind of what the structure of the OpenCV library is like. Core has all of the core functionality. We'll go through in each of these in a little, just very brief bit of detail. But for example, core holds how OpenCV represents images. So when you load an image, it turns it into a matrix, which can then be used within OpenCV's own functions. Okay? And then, for example, HiGUI is the graphical user interface, so that allows you to display images and save them, and that sort of thing. And then we'll go through each of these actually. Image processing is probably the one that you use the most for scientific research, because it includes algorithms for like edge detection, or if you want to do image transforms to make them usable for machine learning and so forth. Yeah, there's some specific ones for example, face detections in the object detection library. Machine learning, I think you looked at briefly in some of the earlier lectures using SVMs and that kind of thing. I think Mark's lecture just touched on machine learning. But yeah, OpenCV has that built in too. You can do training with images, learn objects for detection, so on. It's not just images, it will also process videos. So you can load videos into OpenCV and process video streams. Actually, we'll see a little bit of that later. And some other little libraries like Flan does clustering stuff. Features is the one I've used a lot of, extracting repeatable points from images. Camera calibration, and one of the new ones is GPU for making parallel algorithms, making things run faster, basically. Okay, so that's a lightning overview of the modules. We'll just go into some of the basics of how OpenCV looks at how OpenCV loads images and so on. So in OpenCV, an image is converted into a matrix, and it's indexed so that the top left-hand corner is the 0, 0 index of the matrix. Okay, height is y, width is x. Now you see this image a lot with OpenCV. Lena, I think this was originally used for some early edge detection, maybe edge detection examples. And so it kind of just became a standard image for computer vision, full stop.
It's a picture on the paper.
Yes, it's actually originally from a 1970s Playboy. Yeah, but it's kind of the standard image now. Okay, so yeah, starts 0 here, runs along to, for example, if this is 500 pixels wide, to 500 here, and 500 in the bottom corner. Not that you really have to worry about that unless you're cutting little bits out of images and that sort of thing. Now, color images, you can do, grayscale images will be like a y by x by 1 matrix, and color images will have 3 channels, 1 for each color RGB. But it will handle all sorts of color spaces. Like some people don't use RGB, they use other fancy color spaces, YSV and those kind of different representations, but it handles all of those as well. Now, we're probably going to finish this a little bit early today, I think, but this is the command you've probably already used to install OpenCV for your Anaconda Python installation. So to test that, you can go to your terminal, and if you type in Python, enter the Python environment, and if you just type in import CV2, you shouldn't get any errors. If you get an error after typing import CV2, then it means you haven't successfully installed this group of software that comes in this repository for OpenCV. So you can just give that a go now, because if that's not working, we won't be able to run any of the code. Okay, now do you remember how to use the editors from this morning? Gedit, or Nano, or Vim if you're really, really keen. How about now in your terminal, you can open up a different terminal window from the Python one if you like. How about you open a new file? You can do it from the GUI or you can do it from the terminal. It's up to you. If you need a reminder on how to do it from the terminal, please let me know. Because I want to show you how to run a Python script. So in the previous lecture, you went into the Python interface and you typed in things that you wanted Python to calculate for you or do for you. But you can actually write a whole file, a .py file, as you saw in the last lecture, and run it like this, like just from the prompt, not from the Python terminal. Just run Python, and then the name of the script .py, which you create. And if you put something like this in there, then this function will load an image. So it uses the CV library to read a .jpeg file, and then shows the image using HiGUI. So it uses the graphical user interface for OpenCV to display that image. Then it just waits and does nothing until you press the 27 key, which is actually the escape key. Okay, and then it just gets rid of everything. I know it's a real nuisance to copy all this, so you don't have to. I've actually written it all in this and put it in here so that you can look at it directly and copy and paste it as you like. Okay, that includes the Lena image, loading scripts, and so on. There'll be some bits that we fill in later on in the lecture, but if you can download that first, it would be helpful. I'll write that on here as well. Now, this is where you get to practice using the terminal again, because that's not a zip file, but a tar.gz file, which is the same kind of idea as a zip file in Windows. It's a compressed file. And to open it, wherever you downloaded that compressed archive file to, you run this command, which extracts it into a folder. Okay? Let me know if you have any problems. So the load image script is essentially this. It reads an image. So you'll see that in the script that I've included, this has got the name of an image which is already in the archive, just to make it a bit easier for you. But feel free to download a different image and change it and see how it displays it. Okay. Once you've extracted it, has anybody managed to run this like so? So what did you get? Did you get a picture pop up? So remember the ls command? If you use the ls command, you can see whether you have that file available or not. The load image file. Okay, who doesn't have an image displaying yet? Oh. All right. Now, there's another script in there that converts the image from a color image to a grayscale image. Actually, for a lot of image processing techniques, that's required. You'll need to be operating in just one channel rather than 3 channels. So for the filters that we use next in this lecture is also like that. So OpenCV, it's really easy to do that. It's basically one command. Now, in this script does 2 things. First, it converts the image that we read into a gray image. Now, these things here have now become matrices in OpenCV. Okay, they're now a NumPy matrix of numbers. So here it's still read in as a JPEG file, gets converted into a matrix here. Now we've made a new matrix and stored the output of this convert color function, which takes this matrix and turns it into a single channel. So it combines the 3 RGB channels and makes a grayscale image matrix. Okay, and then it writes it to a JPEG file in this, and then we do the same, showing it just so that we can see what a grayscale image looks like. Now, there is, in that zip file, this script is also included. So if you run that, it will create a new image, a Lena image, but called gray image. And that's the image that we're going to use in the filters. Okay, so have a go at running that. It's called color-to-gray.py. All right, has everyone managed to load that grayscale image? Yes? Because if you haven't, we can't do the next part. We need that gray image for the next part. So the next one we're going to look at is image filtering. Now, for the examples in this lecture, all of the image filtering is done on grayscale images. Okay, so if you haven't created that grayscale image using that color-to-gray script, then please do it now. So there are 4 example filters, library functions that are very easy to use in OpenCV. The first one does a blur, an averaging blur. Okay, so if you run this, it will make the image fuzzy. Now you can change these parameters to make it more fuzzy. This is the kernel size. So this is a 5 pixel by 5 pixel blur. But you can make it bigger to make the image more blurry, or you can make it smaller, which has less effect. Okay? Gaussian filtering is very, very similar. Pretty much does the same thing. It just does a Gaussian blur rather than an averaging. Median filtering and bilateral filtering are a little bit more complicated. But what I suggest you do is have a look in the files and then use this link here for if you want more information. Actually, I should probably put these slides. This link here is just the OpenCV tutorial for filtering. Okay. Okay. So if you look in, you know that those little scripts that you downloaded previously, have a look in this one, filter image. In there you will see a blur, an averaging blur. Okay. Start off by running that, see what it does. You'll see that it makes the gray image a little bit more blurry. And then go back and try these other ones as well. What I will do, so it should be as simple as Python filter image.py, as long as you've saved that grayscale image using the previous script. Okay, has anyone managed to try any of these other filters? See what they do, or played with the parameters for the blur filter? Cool, I think everybody's pretty much got the hang of that. And also notice there's not that much difference between those filter types. So let's move on to edge detection. Because edge detection, you'll see the image changes a lot. Okay, so in that bunch of scripts which you received, there's one called edge image. Which one did it start out with? Let me just check. So edge image starts off with Laplacian edge detection. So edge detection looks for parts of the image where there's a gradient change. And basically it's like the gradient image, where the image intensity is changing rapidly, spatially, then the output is high. Where there's no change, the output is low. Okay? So it has the effect of emphasizing edges, like this kind of feature in images. Okay, so give that one a go. And once you've run the edge image function, also try, it's by default it's Laplacian, but also try Sobel and Canny. This one's a little bit interesting because Laplacian does both directions, but Sobel only does one direction. So you'll only get gradients in, if you run this as is, you only get gradients in the x direction, I believe. Yeah, the x direction. If you change this to 0 and this to 1, then you'll get gradients in the y direction. If you put this to 1 and 1, it will do both. Okay? So this one's probably the most interesting if you want to see something change in the image. Right, if you've successfully managed to run these, can anyone hazard a guess at what this means? This input to these functions, the CV64F? Maybe a little bit, sorry?
Change color.
Not quite, but on the right track. Because now we're looking at an edge image. We went from one channel in 8 bits. So 8 bits means that it's from 0 to 255, the values. Okay? So that each of those pixels can be either an integer value from 0 to 255. Whereas when we're looking at these image filters, these gradient images, these functions don't work in integers. They work in a floating point number. Okay, so the output will be floating point, and it will be between 0 and 1, I think. Not quite sure, actually. But this is a 64-bit floating point number. So it's, yeah, that's what this input is. Now, you could put in something else. You could put in a 32-bit floating number, but they tend to clip when you do that. You won't get the same. You won't get quite the same results. This stores as much resolution as you can for the operator. Anyone managed to get the Sobel filter, the Sobel edge detector working? Not yet? I'll leave that up for a little longer then. Okay, there's a couple of links here to give you more information about how these edge detectors work, if you want to look into the theory of it. Okay, let's keep going. I think everybody's managed to at least run some of those edge detection algorithms. The last one we're going to look at is something a little bit more high level, face detection. So face detection requires a little bit more processing. I've written 2 scripts for you there. The first one takes the image of Lena and does a face detection on that image. Now, if you look into the code, you'll see that it uses a file. It loads an XML file as well as the image file. That XML file contains a pre-trained model, if you like, for faces, which it then applies to the image to find areas which it thinks look like a face. This is quite a complex process using Haar cascade classifiers. So if you're interested, again, you can look at the information on the website, but you can just use it as a tool. You need to do face detection for a particular task. You use the pre-trained model that comes with OpenCV, which I've included in the zip file for you. And then you'll just get face detection working with basically 2 lines of code. Okay, so have a look into facedetect.py first. Run that, and we'll see if you can detect Lena's face in that image. So you can see with OpenCV, something as complex as face detection, which is quite a challenging task from a mathematical point of view, can be done in 2 lines of code by loading a pre-trained model. It's pretty powerful that you can do something that cool so easily. And this is just an example. There's lots of functions like this in OpenCV for doing all sorts of computer vision tasks. So now, I think most of you have got the face detect on Lena working. The next one is a little bit more interesting, I think. It actually opens up the web camera on your computer and takes an image stream, so a video stream, and for each image frame, it does a face detection. Now, if you've got someone next to you, you can sort of get into the field of view of your partner's web camera, and you'll see it will do multiple face detections. So if you, first of all, have a look at the code, see what it's doing, and then when you run it, you can have a play with it and see that it's actually pretty effective at finding faces, even in something as fast-moving as a video sequence. Uses exactly the same model as the previous one. Now, as you can see, this is the script. So yeah, if I turn my head, it's not so good at detecting the face. But this is the script that I've got running on here, which seems to work. So maybe there's a mistake I made in the file I uploaded. Just have a look, see if you can see any differences there. What was the error that it gave? Oh, gray equals. Oh, gray hasn't been defined. I see.
I mean,
Grace.
adding previous into this one? No?
No, that should be okay.
Oh,
Gray. It's this line here, is it?
okay.
Line 13. Ah, okay, yeah, this line here.
Uh-huh.
You don't need this at all, actually.
The
Because
whole
this
line?
is this is from the.
Okay.
Sorry, in the file that I've included, I've made a mistake. Make sure you have these 2 lines here, and you delete the stuff which loads the Lena image. That was left over from the previous file. Okay, so there's 2 lines up here which say image equals something or other and loads Lena, which we don't need to do because we're running a video. So make sure you delete that.
It's good because it wants a lot of
So I think for some reason on your computers, even though this one should be exactly the same, maybe because a mouse was plugged in or something, it's not reading an input from the web camera. Though even after unplugging the mouse and restarting, it didn't seem to work. But exactly the same code is working fine on this computer, so feel free to come and have a look at the web camera and have your face detected. So I'll look into that and see if I can find out what the problem is. But like I said, it's most likely to be the fact that the web camera isn't getting any. There's no images coming in off the web camera. Oh. And anyway, that is the end of this lecture. You can install OpenCV on your own computer relatively easily. It works in Windows too. You don't have to use Linux. and you can try running that face detection on your own computer with your web camera. Maybe you'll have better luck. Anyway, in the meantime, you can come and see it in action on this computer here. Okay, so I'll leave this here if you want to have a look. And that's the end of the OpenCV lecture. So is there any questions about OpenCV in general or anything that we've had in the lecture today? Any ideas that you have that you might want to try and use OpenCV for, perhaps? Okay, if not, then that's it for today. Thank you very much for your attendance.